Let's roll, ladies and gentlemen. Welcoming back once again, Luke Lasater.
Boo! Who's this guy? See, look, I wore out the camera guys yesterday because they put all these lights up here, so I couldn't walk around as much. I guess I'll have to stand back here. Welcome back. You'll all be glad to know that the deck this session is half as long as the other one, so maybe we can not have our eyes glazed over, and because we don't have to talk about audio, video, and lighting. We just have to talk about audio. So if we'll put the deck up for me, then we'll get rock and rolling. We're going to talk about audio over IP management, and we're really going to dive into some of the specifics of audio over IP so that you can have the tools, you can be armed with the tools when you're troubleshooting your systems, when you're trying to think, hey, what's the best solution for me, all that stuff. So we're really going to dive in and look at some of the details and how it works and how they all kind of fit together. So let's get into it. The OSI model, we're going to talk about that. That's the key for understanding audio over IP. We're going to talk about the physical layer, the data link layer, the network layer link, some various audio over IP protocols and kind of how they're working, and then some system design concepts so that you can actually now go and implement this yourself. So, open system interconnection model. This is the framework for all IP networking. All networks utilize are explained by the OSI model, and it goes from the physical layer all the way up to the application layer. So you can see we've got a quick rundown of what those are. The physical layer is basically allowing us to transmit packets over a cable. So that's defined by the physical layer. The data layer, that provides connections between multiple devices. So I've got these two computers, I want them to talk, they're going to talk over the data layer. The network layer takes us up to the next level, and that really will allow us to get in and start talking to multiple computers in other locations. So I want to know what Belmont.com has to say. Well, that's going to utilize layer 3 in order to go out and find Belmont.com and come back to my computer and say, this is what Belmont.com has to say. Then we get into some other ones that don't really, audio over IP doesn't really deal with. We get into transport, session, presentation, application. Don't have much to deal with in audio over IP on those, so we're not really going to talk about them, but just so that you're aware, those are up there. I will say layer 4 transport is used a little bit in audio over IP when we start to say, how do I send a signal from this building on this campus to the other building across campus, and I don't have a dedicated fiber link, right? So we'll talk about some of that. Physical layer, transmitting information over the physical medium. So we've got some components that make up this physical medium, right? And we're going to talk about the physical side of networking, which we're all pretty familiar with. We've seen the cat cables in the cable trays. We've plugged in a computer, into the wall socket. So we're kind of familiar with that part. We're going to talk about the network bandwidth and link speeds. We're going to talk about fiber optic and copper cabling, media converters, and network switches. Those all kind of make up that physical layer. So, speed, bandwidth, right? We know that we have got some different speeds that our networks can handle and perform at. They're measured in megabits per second, which, fun note, there are 8 bits in a byte, so you hear megabyte, megabit. There are 8 megabits in a megabyte, so on and so forth. So we're talking about megabits here. We've got some link speeds. We started off back in the day with 10 base T. That was like, real slow, real small pipes. That's what the small circle is kind of talking about. We've got really a limited amount of bandwidth to push our stuff through. So then they said, man, let's get faster. We've got better technology. We've got better cabling. So then we jumped up to fast Ethernet, 100 base T. And we see fast Ethernet in some of our old school audio over IP protocols like EtherSound and CobraNet and things like that. Then they said, hey, let's get this thing up to a gigabit so we can transmit a gigabit back and forth. And most of our audio over IP systems are running on gigabit with a few exceptions. And so gigabit is kind of the standard that we're all operating at now. Most of the time, you can't even buy a fast Ethernet switch anymore. So it's all gone gigabit and higher. So you can see we're getting larger and larger. We're getting a bigger and bigger pipe. We can fit more and more channels. That's the goal. how can we get 500 channels from our stage to front of house so that you kill your front of house guy, right? How do we get 500 channels from the stage to front of house? We got to have a big pipe. Well, we're not running copper cable anymore. It's not 500 individual, two pair running out there. It's going over a network cable. So that has to get converted and encoded and sent out over the network. And the more channels you have, the more speed and the more bandwidth you've got to have. So we've had a lot of developments since then in the 90s and the 2000s, getting into 10 base to 10 gig and 40 gig and 100 gig. So you can imagine some of these, we can start to really get some pretty serious amounts of channels sent from place to place as our pipes get bigger and bigger and bigger. Let's do a quick little primer on the cabling. All right, so you're going to see, these are the ones you're going to see most common for audio over IP. Cat 5, Cat 5e, Cat 6, Cat 6a. You say, hey, I see at Home Depot this says Cat 5 and this says Cat 6. What's the difference? Well, that's the difference, right? It's how the strands are twisted together. It's the size of the actual copper cabling inside, and it's the rated speed. So we know if we have a bigger pipe, we can fit more stuff through, but also, too, at some point, we got a bigger pipe, we're going to fit more stuff. It's got to also be able to flow at the same speed. If it gets bigger, but it's still a slow flow, that doesn't necessarily help us. So they've had to implement these cables to get higher speeds so that we can get faster throughput so we can send more channels. So you're going to see Cat 5e, Cat 6, Cat 6a. There's two versions on the copper. There's a shielded and an unshielded. All right, and we utilize shielded because it's going to give us the ability to reject electromagnetic interference, RF, things like that that are in our environment. Because we have a lot of important stuff going down our cable. We don't want that to be affected by an external environmental factor. So a lot of times in audio networking, we're typically leaning to prefer towards shielded so that we can protect all those packets that are going through. Because as you can imagine, if you lost a couple of clocking packets, that could be a pretty serious problem in your network. So that's the deal with those dudes. Stranded versus solid core. This is an important thing. You'll see this. Most of the time, patch cables, the short jumpers, are going to be stranded, so they're flexible, they're easy to move. Whereas the backbone cabling, the cabling that's installed overhead and all the conduits and in all the walls, the parts that we can't see, those are solid core cable. And the reason is a couple things. The solid core, we can get a little bit better transmission, but also, too, they're a bit easier to terminate in the field than the stranded stuff. So a lot of times, pre-made patch cable stranded, solid core for our backbone or horizontal, as we call it, cabling. Connectors. So we've all heard of the RJ45, right? Most of us have heard RJ45. Turns out RJ45 is actually a specific way or a specific type of connector that's defined. And actually they've said, hey, RJ45 is a really common term, but really the connector is not an RJ45. It's actually an 8P8C for 8-pin A conductor. So this tells us that there's 8 pins on the connector and there's 8 conductors that go in. So it's kind of like the phase and polarity thing, right? An RJ45 is an 8P8C, but an 8P8C isn't necessarily an RJ45. So polarity versus phase, right? Polarity can be defined. Polarity can be defined by phase, but phase also has a time component that polarity does not have. So kind of a similar thing there. So the 8P8C, you see it as a modular connector. As you can see in those first couple photos up there, you also see it on walls in jacks, right? Neutrik has the EtherCon stuff. There's jacks that connector can connect to. So typically all of our copper cabling is utilizing that. There are some cool special ones, right? Neutrik has got like a ruggedized, the EtherCon, that you can use to plug in for productions and things that you don't want to come unplugged. Also, there's cool proprietary ones. That one up there is made by Link. That one's got two cables in it for network, and it's also got 2 strands in there for power. So you can plug that in, and now all of a sudden, if you're a production and you're running around and I've got to plug and unstuff, portable church, I got to plug and unplug a bunch of cables. I can just get it on this one connector and done, and then we can go on with the show. So there's some specialized things like that as well. We've got be aware if you're going to be purchasing and terminating your own cables, okay, for this system. The Cat 5e and the Cat 6, they're different gauge wire, so they make different connectors for them. So be on the lookout for that. If you've ever gotten a Cat 6 connector and tried to terminate it to a Cat 5e, you'll put it in there, you'll slide it in, and all of a sudden you'll notice that everything's kind of like shifting around in there. And you go to crimp it around, and you go to crimp it, and it shifts off to the side, and then it's like, oh man, I have to cut it off and start over. So be aware of that. Be aware of the gauge of your wire. Be aware of if it's shielded or unshielded. Those are different connectors. So if you're going to start implementing some of this stuff yourself, which if you guys are like me at church, is like, oh, we need to put a projector out here, and it's like, oh, okay, I'll pull the cable and terminate, no big deal. So I'm sure you guys are all doing a lot of that stuff too. So keep that in mind when you're looking at that stuff. There's two ways to pin it out, the A pin out and the B pin out. The A pin out was really popular with the government and horizontal cabling, and then everybody else in the world started using it, and they were like, no, we like B better. 99% of the time in audio and video, you're going to see the B pin out. Don't ask me why they made two, but there's two. And we talked about some of the ruggedized connectors. So those are some important components of the copper side. The Cat5, the Cat6s, there are higher ones, Cat7, Cat7A, Cat8. None of those are really standardized. They're just manufacturers have said, here you go. But 5E, 6, and 6A are kind of the standards that you're going to see. And the biggest point that leads us into the next thing is that you've got a limit of 328 feet or 100 meters. Okay, so if you need to run farther than 300 feet, you're going to run into problems with copper. So that brings us to fiber. Fiber optic cabling, right? So we say I need to go more than 300 feet. Well, then we've got to convert that electrical signal that's run on those copper pins. We've got to convert it to light, because light can run a lot further than our copper can, with much less loss. So again, trying to provide you guys, or arm you with this information as you're starting to think through, I want to start to implement some of this stuff. So what are the pitfalls? What are the things I need to watch out for when I'm starting to think about, okay, I want to do fiber optics. I know that I need to go more than 300 feet. So there's two different kinds of fiber, multi-mode and single mode. And we've got a slide coming up later that'll show kind of what the primary differences are. But multi-mode is typically used for shorter runs. You can kind of see from my chart, I usually say if it's under 300 meters, which is like almost 1,000 feet, right? If it's going to be 1,000 feet or less, then I'm usually going to stick with the multi-mode solution because it's less expensive and it's easier to get a hold of. Whereas if I say, man, I really need to run further, I got to run like across I got to run from this building to the other side of Belmont's campus, it's, a mile away, then I'm going to need to switch over to single mode fiber. So the single mode fiber is able to transmit a lot further with less loss, but the electronics and the fiber optics for it are much more expensive. So most of the time what you guys are going to see in audio is OM3 or OM4. That is going to give us a really great amount of bandwidth. You can see at 10 gigs, we're getting 330 meters. Well, if you divide that down to 1 gig, I mean, that's, basically, we're nearing 1,000 meters for a 1 gig link, right? So most of the manufacturers that are doing fiber consoles, that are doing fiber switches, are going to say, let's go ahead and provide and install OM3. All the Neutrik optical con, if you get the multi-mode version, it's OM3. If you get the single mode version, then it's going to be one of the other single mode options. So be aware of that. Be thinking about that when you're starting to plan your infrastructure and you're thinking, I want to run a fiber cable out here. There are some of the details on the single mode stuff, which we mostly use for audio over IP. Then when we got to go further, we break out into the multi-mode stuff, or into the single mode stuff. Excuse me. All right. Yeah, here it is. Here's the slide I wanted to talk about. So the difference between the two. You can see that we've got the 62.5 micron, the 50 micron, and the 9 micron. So what that means is that's how large the core is inside there. When you have a larger core, that means your light can bounce around more as it travels down that cable. Well, the more it bounces around, the further it has to go, right? So if I'm going from here to here and I go in a straight line, it's, whatever, a foot. But if I go from here and I have to go like this, well, I've traveled like 3 feet to get here. It's the same concept here. Multi-mode, it's less expensive because you don't have to have quite the same precision as you do with single mode. It's still very effective for running long distances, and so that's why we use multi-mode a lot. But you can see some of the differences, and you can see the 50 micron, that's what we utilize in the OM3 to OM4. So you're going to use a lot of 50 micron stuff. And again, this gives us a nice kind of graphic of what it looks like. You can see that the distances that it has to travel is further versus a single mode, which is pretty much a straight on length. So connectors. There are a bunch of standard connectors. So just like we've got the XLR for audio, we've got the 3-pin and the 4-pin and the 5-pin for DMX, right? We've got standards for our fiber optic cabling as well. The most common one that you're going to see is the LC and the SC for installed cabling. Okay, so the LC is probably the most common one. The Neutrik optical con stuff uses the LC. It's pretty standard networking because it's small. It's easy to fit into tight places. You got a device that you need to get 2 plugs into. It only takes up this much space, right? And this is a good point to bring up some nomenclature or some terminology on how many fibers you can get in a connector. So we know when we say, hey, we got an XLR, we know we can run 1 channel of audio over that XLR, right? Well, when we get into fiber, it's typically the same way. You can have 1 strand or 1 run of fiber. While you can put multiple types of networking inside that fiber, it's still 1 strand. And when we talk about Ethernet and networking, we've got to have a transmit, but we also need to receive. A lot of times when you get into fiber, you need the duplex, meaning you've got a transmit and a receive side. And so you can see I've shown the duplex for both the LC and the SC, so you kind of get an idea, okay, it's a 2-way communication that's always happening with our copper cable, our Cat5 cable. There are 8 conductors in there. Those conductors are doing the back and forth for us, and all we know is we just plug it in and it works, right? So you're going to most likely see the LC. The FC was kind of one of the first ones, and then we have the ST that's really popular for production, because the ST is like a tiny little BNC, so it pushes in, it turns, and it locks, and it doesn't come out very easily. So we see that a lot in productions. We see the ST for just general patching in of, hey, I need a patch panel on a wall, and I want to get in and out, and there's a lot of video production or whatever coming in. So they'll put those on the ST connectors because they're relatively inexpensive versus something like an optical con. Right? Most of the consoles that you're seeing that are doing these high channel counts, the Digicos, the Yamahas, some of these others that are doing a lot of huge channel counts are going to have the optical con connector on there because it's a ruggedized connector that's going to protect it, but it's going to allow you to have, in the case of the Duo, it's a duplex, so it's got 2 strands. You got your transmit and your receive. Optical con, they do have other versions that have more strands in them, so if you're using them for more of a utility purpose, I need 4 strands to get from point A to point B. They've got a 4-strand version, all the way up to the 24, the MTP. So that one connector has got 24 individual strands of fiber optic in it. So people really like those for doing patch breakouts, right? I'm going to run a long distance. I'm doing a video system. Each channel of video, each camera needs its own physical fiber to transmit, and I've got like 12 cameras. If I could patch all those into a truck and then take 1 connector to plug in to branch out into all my routers or switchers or whatever, then those high density MTP and other things like that are really convenient. And one of the really, 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 really important parts about fiber is keeping the fiber connector clean, right? So we're talking about light. And if you remember from the last slide, on a single mode, we got 9 microns, right? That's like what happens if a speck of dust gets in there and we've got a 9 micron sized hole. You could have complete loss of light. You could have light, reflected to different areas, and it all doesn't get there. And so then we've got some kind of loss. And at some point, we're going to have so much loss that we're not going to get a signal anymore. So keeping your fibers clean is really important. All of these connectors have a little, it's like, like a handheld thing that you put it in and it cleans it. So it kind of clicks, click, click, click. And it goes in there, and it's got a little tool that goes in and cleans it out. So if you're doing fiber optic stuff, make sure you've got a cleaning tool on hand. All right, any thoughts or questions on talking about the Cat cable, the RJ45, the AP8C, the fiber, and the fiber connectors? Yes, sir.
Does Cat 5, 6, and 6A have the same degradation over 300 feet?
Yes.
Okay.
Yep, that's correct. That's a limitation of copper. So, and technically, if you wanted to take a Cat 6A cable and put it, further than 300 feet, and you wanted to run a gigabit across it, yeah, you may be able to get 350 feet. You may be able to get 400 feet, but you're not, guaranteed that at that point. So it's always best to stay within that 328 foot limit. Cool. Other thoughts or questions on Cat or fiber optics before we go talking about the types of cables that you're going to run into. Cool. All right. Great. Cable types. We're going to talk about some of the installed types as well as some of the types that you're going to see laying across the stage. So these are things to be aware of. Typically, you know, you're going to want to be compliant with the type that you need. We've got CMR, which is a riser type cable. The CMR is kind of the standard that you're going to put into a piece of conduit. That's going to give you, that's a rating on the jacket based on some data that they've done and they've taken to make sure that it's not going to, you know, spew dangerous chemicals if it catches on fire or whatever. So that's the deal with the CMR. The next step up is the CMP, the plenum version. It's designed for plenum spaces, so if you're running in overhead spaces with no conduit, if you're running under raised stages, anywhere where there could be air returns, intentional or otherwise, you need to run plenum rated cable. And this all goes back to a hotel that caught on fire in the 90s. They had all CMR cable. The cable jackets caught on fire. All the air returns were going through all the drop ceilings in the casino, and it basically spread gaseous fumes throughout the entire casino. The government said, we probably don't want that to happen anymore. Let's create some standards that say, if you're going to have them in certain areas, let's have low smoke, let's have minimal, you know, amounts of noxious gases that are going to come off of this stuff if it burns. So that's kind of how a lot of that stuff came about. We've also got outdoor versions, so if you needed to bury it outside, I ran one of these at my house the other day because I wanted my hookup in my office, and the router was at the front of the house. So I came out of the house, I went down and buried it, ran around, came back up, went into the office, right? So there's versions to deal with outdoor and things like that. And then when we get into the armored and the tactical, the armored, you're mostly going to see it with fiber optics. So we know that we've got this tiny fiber optic, it's in a jacket, so it's somewhat protected, right? But then we're going to run that, 300 meters over the top of a warehouse. You know, who's to say that somebody's not going to drive a forklift into that, or that a rat's not going to go up there and try to chew on it? So what they've done is they've started to put them into armored jackets. So the armored jacket is kind of like a flexible, many times they're kind of a flexible metal type of armored jacket that will protect that cable from those external environmental factors. So this can be really convenient. We've done some work with the guys over at Bridgestone Arena, and so a lot of the cable, the fiber optic cable and the cable trays that connects up some of the video stuff is all this armored fiber, so they don't have to worry about whatever happening. Some hockey player getting jacked up and throwing his skates up in the air and cutting all the video off in the venue, right? So that armored cable is the next kind of step up in protection, specifically for fiber. And then lastly, tactical, all the optical cons, all that kind of stuff. There's some kind of metal fibers type things in the cable that give it strength, keep it from getting broken, stuff like that. Again, tactical, really important in fiber. And also you'll see tactical too a lot on the stage with Cat 5 cables, so that musicians can walk across them and they're not gonna crimp down and not work anymore. So those are some of our cable types. So I want to talk about media converters. So I've got a computer and it's 350 feet away from my network switch, and I'm like, dang it, I'm too far away. So either I can string out the cable and have it as a straight taut line from the switch all the way down to my computer, as opposed to coming down the wall and coming over and coming up, right? Or I can utilize a media converter. The media converter will allow us to convert from copper to fiber and back. So if you've got a single device and you're saying, I just need this one device and I need to run more than 328 feet, then you can utilize media converters to convert the copper to fiber. Missing link that can be really helpful, especially for us in churches when it's just like we've got these one or two things that are really far away. We need to get to them. We need to bring them onto the network. Also wanted to talk about the SFP plug. So you've got the fiber optic cable. We need to convert that back into electrical energy. The SFP plug helps us do that, and you'll see that on network switches, which we're about to talk about here in a second. Cool. Any questions on the connectors or any of the types of cabling that we're going to run into? Cool. Arming you guys with some information so that you can be prepared to discuss some of this stuff and have an idea of what's going on. All right, cool. Network switches. We're all pretty familiar with network switches, I think. We've seen them, we've used them, whether it's for IT purposes or audio purposes or it's built into the back of the router at our house, right? We utilize these network switches to hook up multiple computers to communicate with each other. There are two different types of switches. We have managed and unmanaged. We're going to look at those, and we're going to look at why some are better than others for audio over IP purposes. We're going to talk about the different types of speeds and ports and what they'll support and how that relates to our audio over IP network. We're going to talk about how we can get more bandwidth by combining multiple cables inside of connected to the switch to get a higher bandwidth, power over Ethernet, and kind of how planning some of our network hardware can give us the best option for having a stable environment and a redundant environment, even in some cases, so that if there is a failure of a piece of gear, that we don't lose the entire system. Cool. Managed, unmanaged. The biggest deal is that the managed allows us to really go in and tune and optimize our switches for our audio over IP networks. So they've got a lot of powerful features. They give us, there are some specific protocols that audio over IP requires. We'll look at those here in a few minutes. So that gives us the ability to dial those in. We can mix different data types, so we can send audio, and we can send network, and we can send lighting ArtNet over the same switch and not have any issues. We can also create redundancies with these types of switches, and we can also monitor them, so we can know, oh, hey, this port is down. Somebody called me the other day, and they said, hey, this computer's not working. Or, no, it was a console. Hey, this console's not working. So I logged in and saw the switch, and they said, oh, this switch doesn't have any activity on the port. I said, oh, somebody unplugged it, right? So we didn't have to send somebody down to tell them, oh, someone unplugged it. We were able to log in, monitor, and say, something's not plugged in, right? And they said, oh, yeah, you're right. It's not plugged in. So the managed switches give us the ability to support that stuff. Unmanaged switches are great for kind of throwdown stuff. Hey, I've got like 2 or 3 computers I need to hook up just so I can transfer files or whatever. These unmanaged switches are really handy for that. Really small audio over IP networks. I've done like a computer and like one, Dante interface or something on unmanaged switch. That's the only thing that's happening. That'll totally work. They're a lot less expensive, and two, they can be convenient to put out on edge devices. You can put, a bunch of, tiny little, network type things, not audio things, but like, data type things. Plug them into that, and then connect that in to then allow the managed switch to handle that traffic. So that's kind of the two types of switches that you're going to see and that you need to be looking out for when you're thinking about, okay, I want to start planning the hardware for my network. Port types and speeds, lags or link aggregation, and PoE. So you got to know what type of port you have. We talked about the fast Ethernet. We talked about the gigabit. We talked about the 10 gig, right? Different switches, different price points are going to have these different types of ports available to us to utilize. So we want to make sure and watch out for that. And we don't show up, we don't, buy a 52 port, fast Ethernet switch and, want to run, a Dante network or an AVB network over it, because it's not going to work. So we need to be aware of that. And we also need to be aware of if we've got big uplinks. Typically 10 gig we're using that a lot for video stuff, not so much as audio. But when you have a big audio system and you want to transmit, more than 5 or 6 or 8 or 900 channels, you need a bigger link. So we can utilize 10 gig ports as uplinks. So a lot of switches will have 1 or 2 uplink 10 gig ports. And they'll also put a lot of that stuff on fiber as well to help us get that increased bandwidth. So be on the lookout for that, gigabit switches. And if you need a lot of channels to be transmitted over uplinks, you can look for switches that have got 10 gig ports on. And when I talk about this idea that we said, hey, I've got a lot of channels, I want to transmit them, I've got a gigabit switch. When I do the math, it turns out I have more audio channels than I can traverse the single gigabit link. It's like, but I don't need a 10 gig switch. I really just need like a few more megs. I need to just get a little bit past that 100. Well, these switches offer an option called the link aggregation, or a lag. You can take 2 ports, put them together, and now instead of acting as, instead of 1 gig port and another 1 gig port, you put them together, they now act as a 2 gig port. So you can utilize the lag to get more bandwidth to go to between your switch hops, between your multiple switches. And then that way that can save a lot of money, as well as you can create redundancies with that. I think I had a comment up there. Yeah, you can create redundancy. So you've got 2 cables now. And it's treating it as a 2 gig link, but if you keep all of everything under 1 gig that's going over that, and one of them dies, we still got 1 gig, right? So you have created some rudimentary redundancy that way. And finally, PoE, that's pretty familiar, but basically it's going to provide power to your remote devices, your headphone amplifiers on stage for your musicians, your wireless access points up in the ceiling, your personal mixers, that kind of stuff. PoE is utilized to send power to those devices so that we don't have to have 16 wall works plugged into the upstage wall in the sanctuary, because that always looks really nice. Cool. Any thoughts on these conversations about the speeds or the lag or the PoE? No? Good? Awesome. Make sure you get a 1 gig switch. Don't get a 100 base T switch. Network types. These are the kind of the 4 most common that we run into when we're putting together audio over IP networks. We've got our point-to-point, which is what it sounds like. Point A, point B, connect those cables together. Now they can talk. But it's just those 2 devices, right? They're kind of locked in. The next one that we've got is the daisy chain, which is where you have a device that has 2 ports on it and kind of a built-in miniature internal switch where you can connect multiple devices kind of in a straight line like that, and they'll all talk. But of course, as you can imagine, if your audio console is the first thing and you have a link from there to the second stage, the first stage box, and link from the first stage box to the second one, and from the second one to your tracks rig on stage, and that network cable between the first and second one goes down, not only do you lose all those inputs, you've also lost your tracks rig, right? So you kind of are playing a game of chicken when you start to do a lot of daisy chain stuff, whereas it says if it breaks, if a link breaks, if a device goes down, you're really going to affect everything downstream of it. So that's where we love to do star configuration. So the star, or the hub and spoke, that has a centralized switch, and all the devices connect to that switch. So if one device dies or one cable's cut, you just lose them. So oops, somebody unplugged the cable for the multi-track computer. Well, I'm still going to have audio at front of house from all my stage inputs because we're connected to the switch. Of course, if the switch were to go down, that would be a different story, right? Now all of a sudden, all those devices are going to go away. So, hey, is there some way that we could build in some redundancy outside of what our manufacturers may offer us in redundancy? And that's when we can get into a ring configuration. So the ring configuration allows us to connect multiple switches. And I've drawn them as devices, but we should really think about them as switches. We can connect these switches into a ring so that if one link goes down, it's all the data is traveling this way. This link dies, it stops, it says, oh, this one's dead. I'm going to start going back the other way. So now we've got a continuous flow, and really you're looking at only a couple of, maybe a second or 2 of loss of audio as opposed to complete, total catastrophic failure. Most of the time you're going to see the star network. It's really convenient. It allows you to get a lot of individual nodes in faraway places, but still talking to each other. And we'll get to more in some of these configurations later. Thoughts, comments, questions on the configurations? Making some sense. Now we're starting to see, hey, we're going to build up a network so that we can actually process some audio so that our really awesome band can play out of the speakers. So we get into the second layer of the model, which is the data link layer. And it allows us to now not just connect devices together, but now that these devices can now communicate with each other, which is the whole point of what we're trying to do here, right? So we're going to talk about MAC addresses, quality of service, VLANs, multicast, stuff like that. These are really key components in audio over IP networks for proper functionality. If you have some of these missing key components, then you're going to have problems that you may yourself have experienced. So the layer 2 utilizes the MAC address to communicate. The MAC address is assigned by the manufacturer to the device. All right. So every device has a unique ID, and when they come online, they can communicate via MAC address to talk to each other. So that's a really simple way. There's nothing that we have to do to configure anything. It's just plug it in, they find each other, we're off to the races. Next up is QoS, which on the other slide was called quality of service. So most of these audio over IP networks require you to have some kind of quality of service queue. What that means is that we want to make sure that the clock signal has priority over everything else on the network. And then beyond that, we want to make sure that our audio signals and packets have priority over everything else on the network. That way, when John is browsing the internet during the service, because the pastor's going, like an hour long, and he's like trying to update his lunch reservation, right? His traffic of browsing the internet is not going to override the pastor's mic coming over the audio over IP stream. So the quality of service is a really important component to utilize, so that we can make sure that we've got our clocking and our audio prioritized over any other traffic that we may or may not have on our network. So that takes us to this idea of a virtual LAN, or virtual local area network. So you've got a switch, you've got devices plugged in, take a second switch, you plug all those devices in. We've now got 2 local area networks, and they're separated and they're isolated. That's the idea of the VLAN, except instead of owning 2 switches, we own 1 switch. We logically separate that switch in the software so that now all the devices that are connected to these ports are isolated, and all the devices connected to these ports are isolated, and they don't talk to each other. This becomes really helpful when you have a large system and you've got a sanctuary, and you've got a youth space, and you've got a chapel, and you've got hall speakers in your kids' lobby, and you don't want the student volunteers to be going in and trying to repatch your stage on accident because, oh, I didn't realize that I was clicked on the wrong thing, right? So we utilize VLANs to segment out our networks so that people aren't getting access to things they're not supposed to have access to. And also it helps it operate better too, because now instead of this saying, I need to talk to every single device out here, it just says, oh, I only need to talk to the devices in my little area. So that's the advantage and the use of the VLAN. STP, which is Spanning Tree Protocol, that's a requirement if you're going to set up a ring network. So I'm not really going to get into the details of it other than to say it's really convenient. If you plug 2 switches into each other more than once and you're not using a lag where you don't have STP on, then all of a sudden they're going to try to start traversing those links at the same time and create what we call a broadcast storm, which ultimately is going to cause your switch to crash, and it's going to die, and you're going to have to reboot it, and hopefully it's not corrupted where you have to reload the firmware. So the STP is a really handy component to turn on so that if someone accidentally double patches a switch, it's not going to kill it, as well as that's how we can create ring networks using STP. Finally, the multicast. This is a component that's really heavily used in audio over IP networking because we utilize that to communicate our clock signal, and we also utilize that to communicate our device discovery. So when you plug in your console and it automatically finds the stage box and name your manufacturer's software, then that's using multicast to go out and find all the devices and say, here they are, he's here, he's here, he's here, and okay, now we can all talk to each other. But if you've got a large network, that could become problematic, right? If you've got 500 devices all trying to find everybody else all at the same time, and you've got this one little device out here that's like 2-channel amplifier, and it doesn't have a gigabit uplink speed. It only has a fast Ethernet connector on it. Then that little device, every single person's saying, hey, what's your deal? Hey, what's your deal? Hey, what's your deal? He's going to get overwhelmed and crash. So we have things like IGMP snooping and other things like that help us to filter out that multicast data so that only the proper people are getting what they need as far as all these multicast signals. Cool. So that was a brief one, but it's a really important one because most of our audio over IP stuff is all built on top of this, and then we start to break out into some more advanced features moving forward. So any questions on this layer 2 stuff and any of these specific concepts? No? Starting to see, okay, now I can realize, oh man, I can do more than just, plug the mic into the console. There's more. We can start to break this out and have more power and understanding of why we're able to do some of these things. So now we're going to get into the third layer that we're going to look at, the final layer that we are going to look at, which is the network layer. This is going to give us the ability to now traverse multiple networks with our audio signals. We're going to talk about the routers. This is where IP addresses come in, subnets, gateways, and some of these specifics, link local, DHCP, these terms that you've seen, that you've heard, that you've used, they all reside on the layer 3 of this model. So, routers. really cool devices. They allow us to take multiple segmented networks and allow them to talk together with each other. All right. Without it, we talked our VLAN example from earlier. We had this LAN, we had this LAN. They couldn't talk. We said we could do that physically or with a VLAN. But then we decided, hey man, I really want to take these two background music channels from over here and I want to send them to over here. But they're not connected. They don't have any way to talk. So now we've got to utilize an audio over IP solution that can take advantage of layer 3 so that we can then say, I want to take just these two channels. The router's sitting in the middle. The router says, I'm going to pick these up and I'm going to send them over to here, but nothing else. And now we have the ability to transmit across multiple separated systems using our routers. Also, too, you use your routers at home to get out to the internet, right? You've got your local network at your house, and you type in google.com. Really what's happening in the background is it's typing in the IP address for Google server, and it goes out and it says, okay, here it is, and it sends it back to you. And it's doing a very similar thing with your internet traffic that we're wanting to do with our audio packets. So IPv4, we also have heard of IPv6. We're not going to talk very much about it because we're not really using it a whole lot in our audio stuff. But the 4 is made up of these 4 octets, which are up there on the top left. All right, it's called an octet because it's actually 8 bits. So each of those numbers is made up of 8 bits, which we have then converted into our base 10, which is what we're used to, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. So we've got our 4 octets, and those are defined for us for our internal networks. We have a private definition of what those are. So the world, all the servers and the web pages in the world also have IP addresses, but they're external to our system. So we have some specific ones that we are allowed to use in our internal private networks. I listed those up there, 192.168. You've seen that one probably pretty frequently. 172.16 through 172.31. That's a little bit less common, but a lot of IT people like to use that. And finally, the 10 dot range, which is a big open area where we can fit a bunch of addresses in. So those are reserved for us specifically for our private networks. No one on the internet is going to have any of those. If they did, and you typed in 192.168.1.1, and that was some web page, then the web page would load, not the device you're trying to talk to. So that's why they have specified these private addresses for us to use. That's the information on the IPs. We've also seen the subnet mask when we're configuring our network or our computer, right? So the subnet allows us to further isolate our IPs and our computers from each other. So we're starting to get into some pretty kind of things that you have to break out your thinking hats on, just because the representation that we see, which is our base T numbers, right, our 0 through 9, really all that's happening here is down on the bit level with zeros and ones, right? And so because we can't see that, this doesn't make, it's just a bunch of numbers. It doesn't really make a lot of sense. But we'll try to demystify it as much as we can here. So we've got our subnets that allows us to identify what areas, which computers can talk to each other. So imagine it as a playground with a fence. Our fence is this big, and only the people inside this fence can communicate. That could probably be our 255.255.255.0. That means that the 0 indicates that everything that lines up with that octet, that 4th octet over there, it can be any number at once. So we can have 256 kids on the playground. We can't have any more. The kids on the playground next door, they can't talk to each other. They don't even know each other exist. But as we start to change that subnet mask, then now we can allow more addresses into our playground. So now if we bumped it down to example to 255.255.240.0, now we are allowing more addresses in our pool. So we've now just like whatever, exponent of 4 our playground size. So now we can get 4,000 children in there to all play together, and they all know their names, they know who each other is. They can get in there and have a good time. And then you can see we can get all the way down to having as many as 65,000 addresses on a particular private network. And in order to do that, you would need to utilize the 192 range or the 10 range or something like that. So what is the purpose of all that? Why do we want to do that? Why do we want to segment? Well, it's for network optimability, right? Optimization, right? We know we want to optimize our network so that we don't have you know, all of the cars on the freeway at once. We want to stagger the amount of cars that are traveling, because that's important, because otherwise we're going to get a traffic jam, right? Or we're going to have to build a really big freeway to fit all the cars at once. Or we could just say, hey, we're only going to allow 256 cars on the freeway right now, and we're going to build a separate freeway for all those cars and a separate one for all those cars, because they're in other cities. They don't even need to talk. They don't even need to know that they exist. So that's where these subnets and things come in and become important. And so we've kind of broken that down a little bit, but the takeaway for that is just to understand that you can utilize subnets to kind of make your network larger or smaller. And then we'll launch into a little bit of the gateway, which is, you've seen that too. The gateway is just the address of your router. So basically your device says, hey, I want to talk to somebody else outside my network. He goes to the router and says, I want to talk to this guy. The router says, oh, I know who he is. Let me connect you guys up. So that's what that when you see gateway listed as an option, that's what that's doing. All right, cool. There's like a lot of stuff with IPs and subnets. So I know there's some questions about some of this or some clarifications that can be made on some of this. So send them out. Let's do it. Yes, sir.
So where do you get how many sort of addresses you get out of the IP?
Perfect. So I have this note down here. 0 and 255 are reserved, right? Which means that you can use 1 through 254. So you've got 254 of those, and then you add the 2 extra 0 and 255, so that gives you 256. All right. So that would be a .0.0.0, right? Now, like I said, you'll notice that on the second line here, we've gone from 255, 255, 255 to 255, 255, 240. So because we've lowered this number, we've now allowed more addresses to become available to our system. So that's the kind of the way it works. And without a whiteboard to do all the bitwise math for you, which I'm sure you would all love to see, that this is kind of the best way to kind of understand that as you start to decrease that subnet mask, it's going to allow you to have more addresses. Cool. Makes sense? All right, what else? And 256 comes from the bit math, which if you have 8 bits, I don't know who all's familiar with this, but the first bit is 1, the second bit is 2, the third bit is 4, 8, 16, 32, 64, 128, 256. So because of the bitwise math, when you get to 8, that's 256 addresses that are available. So, cool, what else?
If you're addressing any component in your subnet,
Mhm.
do you just you make it subnet like 255, 255, 255, 114 or something, and that gives that specific address?
Yeah, so the question was, when you set that subnet address, which devices do you give the subnet to, right? And how do they interact? So all the devices that you want to communicate must have the same subnet address. So if you've got 254 devices that you want to talk, they all must be 255.255.255.0, and then they all also must be, in the first 3 octets must be the same. So 192.168.0.1 through 254, all those guys can talk. 1 through 254 can talk if that's your subnet. As you start to change it out, right, if we were to drop the 5 down to a 4, so 255.255.254, now we've just opened up a whole nother set of bits. So it could be 192.168.0.1, or it could be 192.168.1.1, because now we've opened up 2 addresses to be available in the 3rd octet. And the math continues on as such. So, good question. Anybody else? Going once, going twice?
So,
Yes.
thinking more like Dante domain manager on this part,
Mhm.
would you do separate subnet groups and then talk with subnet groups?
Yes, you can absolutely do that. And typically, what a lot of times what we do in that case is we'll utilize the VLANs. And those VLANs are basically helping us to break out those subnet masks. So we can have different subnets so that you can talk between .1, .0, and .2, .0, and so on and so forth. So yes, definitely. That's where the subnet mask comes in and allows us to actually physically, or logically, I should say, separate those networks. Cool. All right. Static IPs. We've been talking a bunch about IPs, but let's talk about how we address them. Static, you manually assign it. So you've got a big old Excel spreadsheet that's got every device on your network, and you've gone in and manually put it at an address for everybody. That's the static assignment. Next up, that we're all using a lot these days is the Dynamic Host Control Protocol, DHCP. So the DHCP, oh look, a typo. See, that was a different typo that I fixed. Now I retypoed it to something else. Anyway, just ignore that now that I've called attention to it. The DHCP server knows when a device comes online. The device comes online and says, hey, is there a server out there? And the server says, I'm here. And then the computer says, well, can I please have an address so I can talk to everybody else? And the server says, yep, here's your address. And I'm going to keep track of your address so that when somebody else comes online, I don't also give them the same address. It'd be really confusing. And in fact, I had a friend who got part of his roof torn off because the roofing company went to his house, which was the same number, but a different street of the house they were supposed to go to down the road. So he got half his roof torn off, which he then got a whole brand new roof because they weren't supposed to tear his roof off, right? Same thing here, and you may have seen it before. If you set two devices to the same IP and you connect them to the same network, the computer will pop up and say, hey, there's a duplicate IP on this network. You need to change somebody. So the DHCP will help us to keep track of all those and not ever assign anybody the same thing. The key thing for us is that we really like to know where certain IP addresses are because we've got that application that runs our monitor mix, right? So that we can go into the audience and see what's going on. And a lot of times on consoles, that can only be a static IP, or it can be a DHCP, but then the software makes us type it in every time. So we can utilize a reservation list inside the DHCP server that we can always say the console is always 192.168.1.10. That's always the console. I know I can always get to him. So we can utilize reservation lists in the DHCP server for that kind of stuff. And the thing to note is that if you have a mixed environment where you have some static and some DHCP, the DHCP doesn't know who's static. And so it is possible that it could assign, if you've got a fixed static address of like, .1.100, the dynamic host, the DHCP, all it knows is, hey, I'm supposed to hand out IPs and I gave out .1.99, so I'm giving out .1.100 next. It doesn't know that there's a static out there, and then you're going to get a conflict. It's going to say you've got duplicated IPs. So what we try to do is we say, let's set up a DHCP pool of addresses. We only want to give out .50 through .150 for our DHCP, and then we're going to reserve .1 through .50 specifically for our static devices. So that's kind of some networking things that we can do to help avoid any issues, and we'll utilize the pool inside the DHCP server to define what that is. Finally, link local. Any of the Dante guys in here will have run into this. When you plug two devices into each other, there's no server. They're going to say, hey, where's the server? And then nothing's going to come back. And they're going to say, hey, where's the server? Nothing's going to come back. And they're going to say, guess there's no server. I'm just going to give myself an address. So that's what happens with link local. And the link local range will then allow you to have multiple devices with no server, but where they can still communicate over that layer 3. And so, like I said, the AudNet guys love to say, "I'll just plug them all in and just let it go. It'll be great. It'll auto-negotiate." I had a project one time where they were trying to do that, and I said, "No, we're not going to do that." And they said, "No, it'll be fine." And I said, "What happens if two computers come online at the same time and they happen to get the same address?" We don't know. It's never happened before. There's, 256 times 256 chances of that happening. I was like, okay, cool. It'll probably never happen then. Guess what happened? Two computers came online. They got the same address. I said, what is this, like a 1 in a billion chance that this would happen? And so you got to watch out for the link local stuff. Always be aware that if you're going to use it, there is a minute possibility that could happen. Somehow it happened to me. I don't know, I guess so that I can have a cool story to tell. I was like, I'm going to give you a story to tell at the AES thing, right? Because this insane thing is going to happen to you. So that's the link local thing. And like I said, I don't usually recommend doing that. Let's take charge and manage our own networks because we're all smart. Cool. Any thoughts on any of these layer 3 specific things? I'll go back to this page. Any questions on any of this stuff? No? Good. Sweet. All right. The name of the thing, the reason that you're all here and not, drinking coffee or running away from the coronavirus. We're going to talk about the audio over IP protocols and kind of where each of them land on those layers so that we can be informed to make decisions on what is best for our setup and our hardware and our infrastructure, or how we can pick what hardware and infrastructure we need to use because I really want to use ABB or whatever, right? So let's talk about some of that stuff. Layer 1 is point-to-point. You've run across this with AES-50, right? You've run across this with Aviom ANET, some of the other ones out there. There's networking happening in the sense that there's a cable connected to two devices and there's some packets transmitting over that. There's no negotiation. There's no who's this, who's that. It's just literally the audio and the clock gets sent down at the end of the day. Then we get into the layer 2 stuff. Now, obviously, these are all building on top of each other. So the layer 2 is still utilizing layer 1, but it's adding more features now. So we get into the layer 2, CobraNet, EtherSound, OptiCore, Twin Lane, SoundGrid, DSnake. Those are utilizing layer 2. And that now gives us the ability to have multiple devices on the network talking to each other so that they can exchange audio and clock and what the name of my channel is and, that this microphone has got, 50% battery left or whatever, right? Where they're going to utilize the layer 2 stuff to be able to do this. And then finally, we get up into the layer 3. Layer 3 builds upon layer 1. Layer 2 has all the same features, has all the same abilities, but then they add the additional ability to communicate across networks. So there's a comment about Dante Domain Manager that utilizes layer 3, some of these others as well, so that they can talk across multiple networks so that we can have logically separated networks that are easy for us to monitor and maintain, but we can still send that background music to every building, on campus. And those are things like the ADB and the Dante and the Ravenna and the QLane. So point to point, we just kind of touched on this, but basically it's super easy to design and implement right. I mean, most of us have hooked up like an Aviom or something like that. You just plug it in. As long as there's power, it works, unless you have a bad Ethernet cable, which somehow is always the case. Easy to design, easy to implement. You're typically going to have a hub. The hardware is going to be relatively inexpensive because they don't have to program a bunch of switches or put a bunch of switch hardware in there or anything like that. So that's the point-to-point systems. Then we get into the layer 2 systems where most of our audio over IP stuff starts to become a reality. They're relatively easy to design and implement because we've basically just introduced a network switch, right? And we've programmed this switch to say, I want to make sure that my QoS is good. I want to make sure that my multicast is set up properly. I want to make sure that, if I'm going to use any spanning tree, that all that's set up. Is it complicated to set up? No, not really. Every manufacturer has got like a breakdown list of set these settings. Do you have to dig through the menu on your switch to figure out where those are? You sure do, but you do it once and you know where it's at. So it's pretty easy to maintain from there. And it gives us a lot more flexibility, right? Like I said, now we can start sending more stuff. We can send the channel names. We can utilize, more power to have devices in different places all communicating with each other that don't have to be point to point. We can start to separate our networks out over our space. Like I said, the star and the ring really start to come into play when we're using the layer 2 stuff. Like I said, it can be more robust. We can create a ring if we have a star with multiple switches, right? One switch out here on the stage goes down, right? Maybe only the musicians lose their headphones, but we still are connected. The stage box is connected still to the console, and the console is still connected to the PA. So we can still carry on. We just have to get somebody to go down there and reset the switch so the musicians can hear again. So we can start to create these logical networks with the hardware and our VLANs and stuff. So layer 2 stuff, and then on to layer 3. These are definitely the most complex to set up and the ones that you scratch your head about and the ones where Cisco has CCNA certification to figure out how to set this stuff up. But it gives you the most features. It allows you now to say, I've got the sanctuary, I've got the student room, I've got the kids' hallway, I've got the chapel. They're all separated so that people aren't unpatching my stage on Sunday morning, but I can still program it in to send my background music or send that video feed out to the other areas for overflow, stuff like that. We can utilize layer 3. It's been great over the past few years because manufacturers have said, man, these guys are audio guys, they are used to flipping consoles and stuff. They don't know all the intense networking side, and we don't think they should have to know. And so they've gone in, and manufacturers like Yamaha and QSC and L Acoustics and others have created their own network switches that all have this stuff pre-programmed. So you plug it in and it works out of the box, or you plug it in and you flip a switch and now it's configured for Dante, or it's configured, for AVB or whatever. Or the QSC one, you set it up and go, and it's ready to go for QLAN. So that's been really great. But also too, that comes at a price point, right? So now we got to say, okay, well, we've got to count the cost of that. So that's the deal with the layer 3 stuff. And like I said before, all of these layer 3 solutions are still utilizing layer 1 and layer 2. The clock is still going over layer 2, even though they can transmit it across multiple spots. So that's an important thing to remember. All right, so any questions on this stuff for the audio over IP kind of layers before we get into some design things? Yes, sir. Yes. Dante, Ravenna, AVB, QLAN, WheatNet. Anybody here using WheatNet? No WheatNet users? All right, cool. Well, anyway. And because of layer 3, we can utilize things like AES 67 to communicate between these, because they've have now a way to communicate to each other. So thanks to the layer 3 stuff. Okay. All right, what else? Any other questions on this before we move on to some system design thoughts? No? Clear as mud? Cool. I don't know. I blanked on his name, but Jesus put his hands in the river Jordan and got mud on him and put them on his eyes, and he could see. So I guess mud is somewhat clear for some people, right? So anyway, some thoughts on system design. You say, man, this is so cool. I want to go home tomorrow and buy some switches and buy some gear that can be networked together and run a cable, through the roof of my building so that I can connect some stuff up and we can start, getting, the pastor to another location for overflow or whatever. So let's look at some of these systems and how we can kind of break some of this down and utilize some of these audio over IP technologies. Let's think about like a small chapel, okay? We've got a front of house console. We may have some inputs on stage. And then we have perhaps a computer that is controlling the network, maybe even recording services. And then we have our Dante or our AVB loudspeaker amplifiers. So it's a really simple system. We really only need maybe one switch, right? Maybe it's an AES 50 system. So it's like you got a Behringer or something or another, right? And you're going to connect from your stage box to your mixer console. You've got a single layer 1 point-to-point connection. But then you want to get out to your amplifiers that are Dante. So you put the Dante card in, and now you're going to start utilizing some of those layer 2 functions in order to communicate with your amplifiers. So now we have a flexibility. We're actually running kind of 2 systems. The amplifiers and potentially the multi-track computer don't really know anything about the stage box because it's on layer 1, going over AES 50. So it's up to the console to tell them, hey, I'm going to provide these channels to you for multi-tracking. I'm going to provide these channels to you to send out to the PA. So now we've kind of got a mixed system between layer 1 and layer 2 solutions. But still all valid audio over IP ways to go. And that's pretty expensive, right? I mean, the hardware is inexpensive. It's easy to put together. And now we've really upped our audio quality because we're converting locally at the mic source instead of running 300 feet of mic cable. We're not running 300 feet of mic cable from front of house to the amp room and then connecting to the amp, or we're then running 300 feet of speaker cable from the amp room up to the speakers, right? We can shorten up these links of our audio by turning it into digital audio and transmitting it. So great improvement on the audio quality. Let's talk about maybe somebody that's got a large sanctuary. This is kind of a setup that would be similar to what I have been doing at my place on Sundays. We have got a centralized network switch that's in the amp rack that feeds the amplifiers. So cool, centralized switch, the amps are being fed. At front of house, we have another switch. All the front of house console, the multi-track console, all that is connected to that switch. And then those switches are now connected together. Hey, you're starting to see we're creating a star network, right? We continue on. We've got the broadcast location. There's a switch in there. The broadcast console is plugged in, as well as a console for monitoring the broadcast console software. All that's plugged in at Broadcast World. And then that goes back and connects to the central network switch because both front of house and broadcast need the inputs from the stage, which are on the stage connected to another switch. So now we've created a nice big star network to where if the broadcast room dies, it's not going to affect anybody else other than the poor people watching online who are going to see lips moving and no audio, right? So now we've we've isolated our system to these central points. We've kind of decentralized our failure points, right? And we've created a lot of flexibility because now if we want to add one more thing at front of house, we don't have to pull a network cable, the AM closet, we can just plug it in front of house. Who cares? Whatever. Let's go. Let's do it. Same thing on stage. We want to add some Dante headphone amplifiers, for example. I'll just plug those into the network switch on stage, and now they're on the network. And we can send them our mix from our stage console or our in-ear Clang unit or whatever, right? We've got some options. So this would be kind of a larger system using the Star, and this is really popular. This is like 80% of these audio over IP systems are for churches are looking stuff like this. So you can see it's not a lot of components, it's not a lot of setup, it's pretty easy to digest and implement. But then when we want to get into layer 3 because, hey man, we've decided that we need to send background music across the whole campus, or we've decided that we're going to set up overflow rooms with audio only. I don't know why you would do that, but I guess you could do that. Really, we would set up overflow rooms with audio and video, and we would need to figure out how to get video onto our audio network, which is a whole nother can of worms. But it's there are ways to do it. So, but let's talk about a mid-sized campus. So this is more as opposed to device-specific, room-specific. So we've got our sanctuary, and if we remember our sanctuary model, we've got 1, 2, 3, 4 switches in there. That central switch then has a link out that connects to a centralized AV closet over a fiber link to somewhere in the middle of our building. So now we've been able to take all those sanctuary things, they're connected to the central closet, not necessarily because we need anything from anyone else, but we may want to send something to somebody else, or we may want to be able to monitor what's happening somewhere else from the sanctuary. My office is, if I had an office in the basement of the sanctuary, right, I could connect to that switch to see the whole network, as opposed to having to run a cable all the way out to the central IT closet. So we've got this sanctuary location, we've got a youth room, which has got, maybe is more like the small chapel example with the Dante console and whatever. So we've got that stuff hooked up. So now we can get that on the network. We've got, we already have the chapel, sorry, and then we've got the children's lobbies where they have a bunch of speakers out there, so we want to distribute background music to them. But the background music players in the worship center. So we've got to have the layer 3 solutions, the switches, the ability to, the routers, the ability to transmit across multiple networks, so that we can segment these with our VLANs, but we can still talk across them. So again, it's not particularly complicated as you start to break them down into the smaller sections. I think that's the last thing I have. Yeah, cool. All right, questions on any of these layouts or specific thoughts about what you want to do or what you think you should do or any of that good stuff?